less lately.
Okay, great. So thank you everyone for coming. I'm JD. Today our seminar speaker is Dr. Chris Fox. He got his bachelor's degree from the Rensselaer Polytechnic Institute and Rensselaer, sorry, and PhD in theoretical atomic physics from Penn State University. After that, he was a postdoc at Los Alamos, and he's been there ever since. He is a member of the computational physics division, and he is the primary author of the Los Alamos suite of relativistic atomic theory modeling codes. And these codes are used for, among many other applications, predicting and understanding the electromagnetic transients that result from neutron star mergers, which is a very hot topic these days. He's earned many awards for his work at Los Alamos, and most recently he has been named a Fellow of the American Physical Society. So without any further ado, please give your attention to Dr. Fox.
Thanks, JD. I hope you're still clapping at the end. Thank you for the invitation. My first trip to Michigan. And my understanding, or I learned that Michigan is in the Eastern time zone. So I'm 2 hours away from my normal one. And with daylight savings time, I'm 3 hours shifted, I think. I'm not sure whether I'm coming or going. But anyway, this is the title of my talk, a link between atomic physics and gravitational wave spectroscopy. I am an atomic physicist by training. I know enough astrophysics to be dangerous. So if you ask me an astro question, I will divert it to someone in the audience who potentially knows more about it than I do. And to give you a brief, quick overview, I'm going to talk about half of the time about atomic physics, basic theory, kind of dry, but I feel obligated to tell you a little bit about that so you'll understand how it connects with the astrophysical application of gravitational wave detection and neutron star mergers. Feel free to ask questions if you like. I don't care if we run over. I'm here all day, but I know you all have lives after this. Okay, here we go. Basic atomic physics and opacity theory. This is an illustration I like to show at the beginning of various talks about atomic theory. And this is the so-called classic transmission experiment, where you take a very thin slice of your favorite element and you shine well-characterized light on it, which we'll call having intensity I naught and a particular frequency. It can have all different frequencies. And then you shine the light onto the object and you measure what comes out the other side. We'll talk a little bit more about that as you go along, but that's the basic concept for opacity there. The opacity is going to determine what light gets through and what light gets absorbed. So here is a sample picture of an aluminum opacity at a particular temperature and particular density. I don't really care about those details. What I want to convey is this is the opacity as a function of photon energy. And I want you to realize that there are certain energies at which the opacity suddenly spikes. So the photons of that energy will be very strongly absorbed. And there are other broad regions of energy or wavelength, if you think in wavelength space, that have relatively less probability of absorbing the photons. And so I'm going to try to give you a quick sketch as to how something like this comes about. What's the atomic physics? What's going on at the microscopic level? So what is opacity? It's in sort of formal language, the coupling between matter, this kind of stuff, and radiation, which is coming out of the lights here. And it gives a measure of how much radiation will flow through the certain material. I like to think of opacity as a macroscopic type of quantity, meaning it's related to everyday life, like that classic experiment I just showed. It's something you can measure in a real life experiment. It's not an abstraction. And the amount of radiation that's absorbed in a particular material is just proportional to the opacity, which we use the symbol kappa sub nu. And it's also a product of the intensity of the light. So the more light that hits your object, the more that's going to get potentially absorbed. And the higher the opacity is, the more likelihood it is to get absorbed. So kind of basic linear type concept there. There's also something called an emissivity. If you heat something up, you know that it typically turns a certain color, sometimes very red hot, or sometimes blue or green. So what you're doing is exciting certain electronic levels, and then the electrons are coming back down and they're giving you light in certain wavelengths. So this is just the complement of absorption. You can absorb and then run the camera in reverse and emit. The emissivity is also calculated from these fundamental atomic cross sections that I'm going to talk about in a minute. And unlike the opacity, which has a product, or unlike in the case of opacity, where you take the product of the opacity and the light that's impinging on your material, emissivity is just a quality or a characteristic of the state of the matter you're in. So you heat up your favorite material to some temperature and density, and the emissivity is not dependent on, typically not dependent on the radiation that exists around there. It's just going to radiate and give you free stuff for you to do experiments with or learn about reality. So those two pieces that I just talked about, the emissivity here and the absorption contribution, are what goes into figuring out how the intensity of light differs as a function of, say, position, in this case x, or maybe time. This is a particular example of the radiation transport equation. It's time independent, it's one-dimensional at dimension x, and I've assumed that the radiation is equal in all directions, it's isotropic, and you basically just get this, this simple differential equation. So if we apply this equation to that classic transmission experiment here, if this material is thin enough and cold enough, it won't emit anything in the direction of the beam, or it will be very limited in the direction of where the measurement is going to occur over here. So you can cross that term out, and what you're left with is a very simple first order differential equation. It's the derivative of the thing you want is equal to the thing that you want times another factor. Does anybody know or remember what the solution of that differential equation is? You're shaking your head. How would you call it? Anybody? Exponential. We have a winner. Here we go. Okay. There's your answer. The stuff on the other side, on the right side, is equal to what you put in times an exponential. It has the density, the opacity, and the thickness of the sample. So yes, sir.
So when you define the emissivity, it's a little bit different than other definitions.
Yeah.
You also take into account, you take into account the calculating also what is the probability of thermal emission, for example.
That's what that formula is.
But for example, if you take the Stefan law, usually the emissivity times the black body.
That's buried in there. So in equilibrium, that term would be the Planck function times the opacity, or divided by the opacity. But in general, I can't assume that it's in thermal equilibrium, so I've just written it as epsilon. And it would have sort of, it does, yeah. I swept a lot under the rug for the purposes of this talk. There are several parts in this talk where I will say things like, oh, that's a whole nother lecture. I've had to simplify certain things in order to just convey the basic result. Okay, so the idea is, if you could have a perfectly thin or appropriately thin sample of your favorite element, you measure the light that comes out, you know what went in, you can take a logarithm and get the opacity downstairs, you know the thickness of the material and density, and you can get the opacity. It's easy to say the words, it's very difficult to actually measure opacities for a variety of reasons that I will not go into in this talk. A useful physical quantity is that factor, or that product rho times kappa. 1 over that has the dimensions of length, and that is the mean free path, the optical mean free path, meaning that's roughly the distance a photon will travel before it undergoes an absorption or some kind of interaction. Okay, so that was the macroscopic opacity part of the talk. Let's connect it to the fundamental atomic physics underlying that quantity. So here on the left, another cartoon type diagram. On the left, I have a grid that represents whatever I want to model, maybe a piece of a neutron star or this table or whatever. And I've put a grid or a mesh, and in each grid, from a computational point of view, it's characterized by a certain density, rho. There can be a temperature. And as an atomic physicist, there are these things that we call N sub IL. Those are the atomic level populations, also called a number density, because it has units of 1 over volume, or dimensions of 1 over volume. Typically, we use 1 over cubic centimeter. What is this kind of thing? Well, if I know there's a lot of nuclear folks in the room, this is essentially how many ions live in a particular level of my problem, energy level. So if you're not sure what I'm talking about, let's move over to the right-hand side here. This is a cartoon energy level diagram for a generic atom. So remember, I'm an atomic person, so we're dealing with the electrons going around the nucleus, not the nuclear stuff, but same basic concept. So here we have, in this column, the neutral ion stage, meaning if it's hydrogen, you have one electron, and that electron is in a certain orbit, but there's an infinite number of orbits there, given by each one of these horizontal lines. So I start with the ground state, first excited state, and so on. If I had a more complicated element like helium, which has 2 electrons, well, I can have 2 electrons going around, which will have an infinite number of levels. If I apply enough energy, one of those electrons is free, and now I only have 1 electron around the helium. That's called singly ionized helium. And then if I popped both electrons off, I would have doubly ionized helium, which is a helium nucleus. And that would be either doubly ionized or just the helium nucleus. If I had uranium, which has 92 bound electrons, I would have a column for 92, and 91, and 90, and so on. I would have 93 columns like this, each one of them with an infinity of levels, except for the boring one at the end, which is just a nucleus. So the goal of an atomic physicist, one of the goals, is to measure for a plasma, for a certain temperature and density, how many are in each one of these levels. That's the game. And once you get that information, you can calculate opacities and things like that. So in the plasma, you've got photons, you've got bound electrons, which are orbiting around a nucleus, and you have those electrons that have been freed somehow. And as I mentioned, the idea is to use these players to calculate the populations. And then from there, you can get an opacity. And if you're a hierarchical type of thinker, here's a high-level view of what I'm talking about. I'm not going to go into much more detail. The atomic physics part of the talk is almost done, okay? At least the basic boring part. So this would be, you solve the wave functions at energy level, so you would solve the Schrodinger equation, or if it's a relativistic system, the Dirac equation. From there, you would take the wave functions and calculate cross-sections. So we're talking about matrix elements. So we have a bra and a ket and an operator in the middle, like the dipole operator, things like that. So that gives you the probability of going from one of those levels to another one of those levels. So there's probabilities of jumping between these, which we'll talk about in a minute. Once you get those cross sections, you can come up with a rate coefficient, or the number per time that happens between one level and another for a given process. You use those to build a system of equations that couple all of those levels. You solve that system of equations, and you get your populations out. Once you get a population, an opacity is essentially just a sum of all the different populations times the cross section. So you're starting at a certain level, you're ending at a certain level, and I need to know how many of these things I started with. The more of them I started with, the more chance there is of it happening. If I have none of them, there's no chance of it happening. If I have a lot more in a particular level than another, then that will increase the probability of that particular process happening. So the solution of those equations is sometimes referred to as atomic kinetics modeling. This is I'm trying to contrast what I do in atomic physics with what folks typically, but not always, do in nuclear physics, to touch base with something you may be more familiar with. There are far too many of these atomic processes for us to measure experimentally and get cross sections and plug them into our modeling. So we typically rely on ab initio calculations. In general, there aren't many experiments, even if we would like to use them. Nuclear physics folks, at least the people I deal with, talk about evaluations where they build tables of data or recommendations which rely on both experiment and theory. That's not common in my field. And as I mentioned, the atomic data are typically calculated from first principles. There are some, there most certainly are. They're, I would say, just limited. The ones that we have, we compare to as many times as we can, maybe more often than we should. But when you want to calculate, there's an infinity there. We typically have to cut it off somewhere. But imagine, for the example you're going to see in the back end of this talk, there will be on the order of 1 million levels. There are no experiments that measure millions of levels. We would love to have it, though. So going back to the simple cartoon diagram, we have an example just with arrows of excitation, de-excitation. So if you started in this ground state and a free electron came around and said, I'm willing to give up some of my energy to bump one of those bound electrons into a higher orbital, that's illustrated by that green arrow there. Similarly, once you get up to that point, you have this bigger orbit. The electron, as you maybe know, in fact, one of the professors I spoke to said you are supposed to know about spontaneous radiative decay. You just had a midterm and you're probably tired of it. But if you're up there, that electron can spontaneously say, I want to go back down to where I was, and in order to conserve energy, I will emit a photon. And that can happen in any one of those ion stages within any one of those columns, and they have different energies and so on. Yes, sir.
How often do you have to deal with a system that's not really thermal?
That's a good question. How often is a tricky question to ask. I mean, I'm asked to model a lot of different plasmas. I would say 30% of the plasmas I model are not in LTE, but many people say, I can't afford that calculation. We'll do it in LTE anyway. So maybe 30% of the time. So just as you can go transition between the levels within an ion stage, you can also go across them. If you go in that direction with the green arrows, that's called ionization. You ionized an electron. If you go in the other direction, you've recombined. A free electron said, oh, I'm going to recombine and become a bound one again. So you can go in both directions there. You could jump 2 or 3 or 4 or 5 ion stages. The probability of the cross-section for that is quite low compared to just one ion stage in either direction. So we often ignore that, but for certain exotic cases, that may be important as well. So the goal, as I mentioned in one of the high-level cartoon diagrams, was to build a system of rate equations that couples all of the levels. And what you end up with is a first-order time-dependent equation for these populations. And basically, the time rate of change of any one of those populations is equal to all of the ways that population can flow into that level minus all of the ways it can flow out. And in matrix form, if you're a matrix fan, this is the vector you're trying to solve for, and this is what's called the rate matrix, and that's where all the really cool atomic physics is. And this matrix can be as small as 10 by 10 for simple systems like hydrogen, or it can be as big as technically infinity by infinity. The biggest ones I've solved are about 100 million by 100 million, which is a very sort of one-off kind of calculation. So let's talk about a special case which relates to the question. Yes, sir.
Just real quick,
Yep.
I'm curious, for that one-off calculation, like if it's appropriate, I'm just curious,
Yeah.
what was the benefit? Like, did you, or whoever, like,
What was the?
what do you get out of doing a calculation?
You get a much higher fidelity spectrum. So imagine we have an infinity of levels, and you can play games like, the experiment only has a certain resolution. So I can't really refine features on this scale. So I'm going to average over them ahead of time and shrink the size of the matrix from million by million to 10 by 10. The price you pay is you get this really blobby spectrum. And somebody else calls you up and says, no, I need all the detail because I have a killer spectrometer. That's why you would do something like that. It's pretty rare, but it happens. Okay. So let's talk about a very specific solution to these equations, which connects to his question. If you're in something called local thermodynamic equilibrium, and that's a whole nother lecture. I don't have the time to go through it in detail. We refer to that as LTE. If you are, then typically it's characterized, you can characterize the temperature, the plasma by a single temperature, and the electrons have that same temperature or characterized by that temperature, and the radiation is also characterized by that temperature, and the ions which are floating around also by that one temperature. If you have that special case, and again, I'm not going to go into it in detail, then the following bullet is true for solving the populations. You can use the Saha equation, which means that any one of those populations is essentially proportional to an exponential that has its energy and the temperature. So somebody called you up and said, this is the temperature for this plasma, 10 eV. Then you go to your atomic physics code or tables where you have all these energies, you plug this in, and you get the populations. You don't have to solve that system of equations. Life is much simpler, orders of magnitude in time simpler to calculate. It's a very easy thing, relatively speaking, to do, and it's often applied even when it's not valid. But You don't have to consider all of those fundamental processes and cross sections I talked about before. We have a database of LTE opacities that have the first 30 elements of the periodic table. It's currently under construction. It's been down for several months, but it's close to being launched again. And so that aluminum example I showed, that random example, came from that database at the beginning of the talk. You can query that if you like and use it for your applications, or call us up or send us emails if you want to use that in more detail. Okay. Yes, sir.
What is the accuracy of this kind of approach? 1%?
It depends on the element. So for hydrogen, where there's only one bound electron and we're pretty confident, 1% would probably be good. If you're dealing with the lanthanides, which will be at the end of the talk, now you're in the 10% to factor of 2. Yeah. So we're dealing with the n-body problem trying to solve, and we like n equals 1. N equals 50 is a lot harder. Okay, let's shift now to the astrophysics part of the talk so I can talk about something that I know enough to be dangerous about. So unless you've been living under a rock for the past several years, we've entered the age of gravitational wave spectroscopy. 2015 was the first gravitational wave observation. It was published in 2016. It was called a binary black hole merger. So binary tells you there were two of the things, two black holes merging. It was measured by something called a LIGO. And if you read a little more into the abstract, it matches the waveform predicted by general relativity. So that's pretty fundamental stuff. Fast forward to 2017, now we have both gravitational waves and electromagnetic waves being measured from the same event. This was extremely exciting. Again, you see gravitational waves, you see LIGO, another detector called Virgo, something called a gamma ray burst, which is electromagnetic radiation. And let's see, the observations support the hypothesis that this was the merger of two neutron stars followed by gamma ray burst, and something called a kilonova or macronova powered by R process nuclei. And since you are nuclear folks, you probably know more about the R process than I do, but I will talk about it anyway at some point. So let's talk about what these events come from. A simple stellar evolution chart. You start with a stellar nebulae, and you can go the top path, which is sort of the lower mass stars, or the bottom path, which is the massive stars. Top path typically ends in a white dwarf. The bottom path typically has two options. The first one is a black hole, which was how the first gravitational wave was observation was made. And the second one up here is the focus of the remainder of this talk, which is two neutron stars merging. So just a quick joke, which I've said to one person I talked to today. I naively thought, as an atomic physicist, I do collision physics, electrons colliding with ions, et cetera, that the two black holes that merged found each other in the universe. There was one formed by a star dying, and another star died, and then they collided. And my astrophysicist friend said, no, Chris, the space is really big, and the probability of two black holes finding each other is almost 0. So they told me that roughly 2/3 of stars are created as binary pairs already, and somehow they both die, and yet they still remain close enough together to merge again. So that's how you get two black holes merging or two neutron star merges. They started as binary pairs. Sorry if you all knew that, but I didn't, so I had to share that. Okay, so as you may be familiar, that gravitational wave observation, the first one came from a LIGO device, which is, we have one located here in Louisiana and another located here in Hanford, Washington. It takes light a fraction of a millisecond to go from there to there, so it checked the box that was something of light speed that was found there and there, such as a gravitational wave. If you've never seen a picture or been to the Hanford or Louisiana site, this is what the LIGO looks like. Each leg is roughly 4 kilometers long, and it's basically a very large Michelson-Morley type experiment. If you don't know what that is, if you've never encountered it, it's just sending light down both legs. You shine a laser or some light source, it hits a beam splitter. One beam goes that way, one beam goes that way. They bounce off mirrors, they come back. You recombine them in some manner. And if you believe the literature, it sounds like science fiction, the LIGO can detect changes in distance on the order of the fraction of the dimension of a proton, which seems impossible to me, but they claim that's what it can do. So I'm obligated to believe them. This is a chart that I figure I like to show off. I pulled it off the internet, and it measures the strain rate, which is related to the displacement of those arms of the LIGO versus the wavelengths that can be measured for different objects and also for different observation tools, such as LIGO. So here's the LIGO that I just talked about. The mind-blowing thing for me on this plot is it's measuring wavelengths, things of wavelength of 1,000,000 meters, a megameter. So I live way down there. I make a living, and most of you who do nuclear physics, we're dealing with wavelengths that are significantly smaller. So two very different scales are combining in this neutron star merger type of field here. Now some history of gravitational waves. I like to talk a little bit about where things came from to show younger folks the development of how quickly or how slowly certain fields come about. About 100 years ago, Einstein predicts the existence of gravitational waves via general relativity. 60 years later, Russell House and Joseph Taylor infer the existence of gravitational waves from a pulsar. The pulses were changing in a very predictable way, and they were consistent with the two objects orbiting each other and decaying, the radius decaying at a certain rate and giving off gravitational waves to conserve energy in just the right amount that it matched what was predicted from general relativity. Not a direct observation, but a very exciting a prediction for which they won the Nobel Prize about 20 years later. Russell House was a graduate student when he did that work at the University of Massachusetts. It's not common for a graduate student to be given a Nobel Prize. In fact, there are at least a couple of examples where graduate students probably should have won a Nobel Prize and didn't, but he was one of the fortunate ones. I believe he'd already left the field of astrophysics because you couldn't find a job in astrophysics, and yet they gave him a Nobel Prize. Also in the same year that they inferred the gravitational waves, Latimer and Schramm proposed that this merger could be a place where our process elements are produced. Moving along to modern day, just a few years ago, we've got at least 3 to 4 gravitational wave observations. 2017 was the neutron star merger observation with both electromagnetic and gravitational waves. Another Nobel Prize about 40 years later to Weiss, Barish, and Thorne. And then about 2 weeks after that was the worldwide press release for that observation there. So things have been moving very rapidly in modern time. 100 years went by, maybe 60 years something happened, then another 40 years. And here we are today at a pretty exciting time. So why should we study neutron star mergers? In addition to the existence of gravitational and electromagnetic waves in one event, they are suspected to be the source of these really short, less than 2-second gamma ray bursts. And as I mentioned, they are hypothesized to be what is called the site of the R process. I'm in nuclear physics land here, so I feel obliged to show you this plot. I'm sorry if you know it. I'm sure you know it better than me, but the basic idea is less than 300 stable nuclei. This is proton number versus neutron number. The R process is a neutron comes in. It's considered rapid compared to the slow process, so that's what the R stands for. It interacts with Z protons, and out comes Z+1 protons. So you can ratchet your way up this diagram and then eventually fall into the valley of stability here. You knew that, though. Another reason to study neutron star mergers is we haven't yet been able to predict the abundance of neutron-rich elements that we see, for example, in the crust of the Earth or in the spectra of stars. And if you look on the internet, you can see figures like this where it assigns each element a certain astrophysical object. And here are the lanthanides and the actinides, and you can see in this picture here, a good bit of them are orange, which is connected to supernovae explosions. There's also some man-made ones there and some from large stars. However, that picture is not entirely correct because supernovae can only predict about half of the abundances that we know exist in the Earth's crust, for example. So my advice to the young folks, don't believe everything you read on the internet. Now you can find updated periodic tables where you now see purple here, and that's connected to neutron star mergers. This is not a guarantee still, but it's more and more likely based on the current observation that we have. that we have an additional explanation for where these heavy elements can come from. Okay, some very basic characteristics of neutron stars. Neutron star mergers, there's an axis of rotation. They're spewing out, after the merger, they're spewing out these, this ejecta, which is made of the heavy R process elements, or hypothesized at least. And there's heavy velocity shear due to the rotational motion. So that means at any given point, the change in velocity, or the velocity is changing very quickly, which means as an atomic physicist, if you have a certain opacity to absorb the light, there's going to be, the lines are going to be Doppler shifted, and so that has to be taken into account. What else? You also need to think about an angle of inclination. If this happy faces the Earth, you're not guaranteed that every one of these rotations occurs in just this plane. It might be tilted towards you, away from you, so there's a geometric effect, which you have to take into account when you actually observe light from one of these objects. What sort of so-called light curves or spectra can we expect from one of these objects? So up until this recent measurement, no one was sure. We're still not entirely sure. But if you're a supernova fan, you can look at the light curve. So that's the magnitude of the light, or intensity, as a function of time, in this case days. And to me, as an atomic physicist, my untrained eye, I just kind of put them all on top of each other and put the peak intensity at 0 days, and they all look roughly the same. I'm sorry if that's offensive to the astrophysicist, but to me, as an atomic physicist, that's what I see. And they have different names, 1A, 1B, etc. I don't know what they all mean. But the purpose of this talk, what I want you to come away with is the light curves the peak lasts for about tens of days at most, and then they decay very rapidly. And each one of the points on this light curve is the integration of a frequency-dependent emission spectrum that happened at that particular time. So for neutron star mergers, the modeling typically predicted a light curve that was similar in shape to what you previously saw, but reduced in its peak brightness. So it was reduced compared to a supernova. It's about 1,000 times brighter than a classical nova, and that's where the name kilonova comes from, 1,000 times more. So more generically, if you just want to say it's something bigger than a nova, you would just say macronova. This term has caught hold more in the literature than this one, but you'll see both. And as I've mentioned, and we know, we have precisely one observation for neutron star mergers, and folks have been trying to fit it in various ways, which means it doesn't really constrain the theories very much. There also isn't much opportunity to do detailed line spectroscopy to say, oh, that element is definitely there, and it's there in that percentage, or that one's there. Things are just starting. We'll see if they continue. So here is a picture of the light curve from that first observation. Let me go back for a second just to remind you. This is well-known supernova light curves, and predictions and observations agree to at least this qualitative degree. And neutron star mergers were expected or predicted to follow this same trend, just lower in magnitude. That's not what we saw. It's monotonically decreasing. So this is essentially luminosity as a function of time. It doesn't have that rise and fall. We'll talk a little bit about why as I get to the latter half of the talk. This is the model, standard model, not the only model, but a typically accepted one of what a neutron star merger was composed of before the observation. So you start with a short gamma ray burst on axis. So this is the axis, and here are the two, the ejecta of the neutron stars, which eventually are predicted to collapse into a black hole for this picture. After the gamma ray burst, there's something called an afterglow, where X-rays are expected to flow in this general area. While that's happening, there's this expanding ejecta. And it's made of, or hypothesized to be made of, our process elements, which are radioactive. And so the nuclei are decaying, and there are gamma rays coming out. And those gammas are saying, I want to get out of here. but there's all this heavy element ejecta saying, not a chance because I'm going to absorb you because I have a very high opacity. Eventually though, the ejecta is going to expand to the point where it will become optically thin. There'll be so few elements per cubic centimeter that the photons will find a way through. Or just by the nature of the opacity decreasing because the density decreases, there are fewer absorbers, the light will also escape. So here is a copy of a figure or diagram from the 27 APJ letter concerning the neutron star merger. On the x-axis we have time, and it's compressed here, it's orders of seconds or tens of seconds, and then it expands to days. So this is 1 day here, and this is tens of seconds early on. And on this column or axis, we have the different kinds of radiation, gravitational waves, gamma, X-ray, UV, and so on. And then underneath them in tiny letters are the satellites that made the observations. So the gravitational waves were found by or observed by the LIGO detector, and also not found or barely found by the Virgo detector in Europe. And simultaneously, or almost simultaneously, there was a gamma ray discovery. So this is a telescope that's Fermi telescope scanning the sky, and it saw a burst. So we got lucky. These two saw something, different kinds of radiation, saw them. There was a sort of a coincidence discussion that went on. I don't know the details of it, but basically that caused all of these other telescopes to be alerted to look in the different wavelength ranges of the electromagnetic spectrum. And look at that, we see each one of these colored bars is a specific detection at a certain time in that particular wavelength band. So we saw, I will say, everything in quotes. That was quite wonderful and surprising and scary all at the same time. So after that observation, based on the fact that we saw radiation not only in the X-ray and in the infrared, but everything in between, it caused this new hypothesis to be put forward. First, because of the strength of the gamma ray burst, or actually the weakness of it compared to others, it was consistent with a 30-degree angle of inclination compared to relative to the Earth. So that's shown here by 11 to 33 degrees. It's closer to 30 based on current analysis. In addition to the gamma ray burst, the expansion of the ejecta was occurring, and the hypothesis is something else was going on along the axis in a cone to allow light of more energetic photons, bluer photons, to escape. There are different, I would say, predictions or models to explain this at the moment. One of them is neutrino winds. So neutrinos definitely exist, and in this particular scenario, and they are resetting the nuclear interactions, for lack of a better phrase. And so not all of them are making it to lanthanide status. And so you have potentially a cone of lighter elements, which will allow different kinds of light to escape compared to the red or infrared light that was predicted to escape here. So that's one of the leading models, if you like. We only have one data point, so nobody really knows for sure. Moving along, I'm trying to, so now I've gone to the observation. I'm going to try to reconnect it to opacities now to say, what does that have to do with what we've seen? Here is a model of the mass fraction or abundance of all of the elements that are predicted in the ejecta, in the expanding ejecta. And you can see that they are lanthanide rich and actinide rich. I'm not an expert in this type of simulation, but it came from using a chain of nuclear cross-sections, among other things, some of which the cross-sections are known, and other of which I'm sure they don't know, so I don't know what they do in that case. But you can see nuclear physics figuring prominently. So now I'm going to walk you through the calculation of a sample lanthanide opacity. It's kind of funny. I show this picture when I'm giving this type of talk to an atomic physics audience. I have to remind them that I'm down here. I suspect many of you are used to looking here, but we typically don't look down here at all. And they say, what were those two rows again? I can't remember. And anyway, as Jaydeep mentioned at the beginning, I'm a co-author of a certain suite of codes called the Los Alamos suite of modeling codes. You can run them online. Again, the website is down. We're slowly working on getting that back up. But it has a bunch of codes that allow you to calculate energy levels and cross sections and things like that. And this code is not available, but that's the one that we use to calculate the opacities and the emissions. So this is the code that solves that system of equations in either LTE or, as he asked, in non-LTE scenarios. All right, so physical conditions for a neutron star merger. When the merger is occurring, we have temperatures as high as 1 million electron volts and densities that are 10 to the 14 grams per cc. So these are sort of science fiction densities for someone like me, an atomic physicist. Once the expansion occurs and the light starts coming out, now we've cooled down significantly to only 1 eV, still much higher than room temperature, but much cooler than this. So that means there's going to be bound electrons. Now, at 1 MeV, that will boil off bound electrons from any element I'm familiar with. The density has also become much lower. It's decreased by 20 to 30 decades. So because you have these heavy elements at such cold temperatures, you're dealing with either singly ionized or 2 times ionized or just a few times ionized. So they have 50 to 70 bound electrons if you're dealing with a lanthanide. This is extremely hard to calculate in my world. This is the n-body problem where they're all talking, all these bound electrons are talking to each other through the Coulomb force, and they're also talking to the nucleus. So for what I'm about to show you, I'm assuming local thermodynamic equilibrium that may or may not be correct for these conditions. That is a whole nother talk, but for the purpose of this talk, let's keep it simple, and I will show you what you get. And in particular, I'm going to focus on just one element, samarium. I could have chosen another one, but this is just the one that I used for this talk. So I chose a characteristic density in the ejecta of 10 to the minus 13. And here's the temperature varying. And this is what's called the ion fraction. So this is how much exists in one ion stage. My early diagram, my energy level diagram, column number 1 is neutral. This is how much of it exists, samarium 0+. It exists as 100%, and then it quickly falls off as the temperature increases because I've ionized 1 electron as the temperature needed. So now I have samarium 1+. It exists for a certain temperature band, and then it falls off, and then 2+ and 3+ exist, and so on. This is the way standard plasma physics goes. So what about opacity? Well, the earliest astrophysical attempts to guess at the opacity used very simple models, and they assumed that the free electrons that are floating around in the plasma will be responsible for the opacity. That's often an important and significant and good assumption if you have hydrogen, which is common for many astrophysical applications, because hydrogen has 1 electron, and once it's boiled off, the electrons are a main component for interacting with photons that come in. So they tried that in this case, even though we know that there are a lot of bound electrons. And what you get is a simple flat curve. I have different temperatures up there, slightly different, that focus on different ion stages. You get roughly the same behavior for the opacity on the y-axis for all photon energies. So there's no discrimination of absorption for using this model. A photon of this energy has the same probability of being absorbed as this one, and so that doesn't predict any difference in the way the light will be treated if you use this model. But as good atomic physicists know, there are bound electrons, and there are a lot of them in this case. So for the 4 ion stages I consider, and that's chosen, those 4 ion stages, 0+, 1+, 2+, 3+, are what's expected to exist at this temperature and this density. The other ones won't be there because there isn't enough energy to ionize. I plugged in some simple 25 electron configurations. Don't worry if you don't know the details of what this means, but it's just a handful of configurations, and what pops out is 100,000 energy levels. That is a large number of energy levels for such a simple characterization that I can put in one view graph. This is unlike anything that I typically deal with. With hydrogen, it would just be 100 levels or something like that. And in addition, they can talk to each other through radiative decay. There's 1/3 of a billion radiative transitions. These are very large numbers compared to what I'm used to dealing with. So when you add those in, the boring scattering curve, which was way down here, suddenly gets enhanced dramatically by those bound-bound transitions, meaning a bound electron jumped to another orbit. And that difference is, what, almost 10 orders of magnitude. So now suddenly the probability of photons in this range of making it out goes way down. The lanthanides are going to say, sorry, I've got so many energy levels, I'm just going to absorb you. The gammas started out as gammas. They got downscattered. They started out way over here, downscattered, downscattered. Eventually they find themselves here, and they're right on the brink of finding an opacity that's low enough to escape. But one of the important questions is, what kind of light will escape? Will it be in the optical, because we've got telescopes that can measure that? Will it be in the IR? We've got maybe fewer telescopes, and they're more expensive to build if it's out there. So just to guide the eye, I've put the visible or optical window there. That's a few EV. And you can see that that's the band that's typically absorbed the most. So from this prediction, if you had a lanthanide or samarium ejecta, the prediction would be, I don't think you're going to see much optical. We did see optical in the observation, but from this prediction, we didn't. So for part of my work, my contribution to this field is to calculate all of the lanthanide opacities, and I've done uranium as the first actinide. So here's uranium in the lower right, and I've just chosen 3 sample lanthanides. This is samarium, which we already dealt with. And I've chosen 1/3 of an EV, and again, that characteristic density, which I like because it's stuck in my brain for some reason. But the basic idea is each one of these is opacity on the y-axis, and then the same photon energy grid. They all have roughly the same kind of shape as what I showed you before, right? They have dominant opacity in the optical around a few EV, and they fall off as you go towards lower wavelengths, lower energies or higher wavelengths. Don't worry too much about this particular edge here. It's not relevant for this problem. It should be, there's another model that kicks in to downscatter the gammas to get to this point. So I apologize for that, but don't focus on it. They all have basically the same look, but they're different in detail. If you look carefully sort of in the 0.1 EV range, sometimes you can see a dip there, and you see maybe a dip there, but it's higher, and then you see a forest of lines. If I compare these two, these are what are called homologs. So they appear one above the other on the periodic table. So they have roughly the same electron structure, except the principal quantum number is higher for uranium than it is for neodymium. But in a hand-wavy sort of way, an atomic physicist or an astrophysicist might say, well, I can use this as a surrogate for that one because they have roughly the same. Maybe I have to scale it by the atomic number or something like that. That's not necessarily true, because you can see a lot more structure here than you can here, and you can see that the magnitudes are different. So our goal is to try and put this on a more precise footing by calculating all the details. Most of the modeling up till now is typically used neodymium as the poster child, as a sample lanthanide, to represent all of the lanthanides that exist. That you saw in the models, there are actually, all of the lanthanides exist to some extent. Yes, sir. No, there are energy level measurements for a small number of lines. Yeah, so this connects with, gives you an idea of what we're dealing with. We've got 1/3 of a billion transitions and a handful of lines from the NIST database. Now, one of the saving graces is when you do a calculation, when you do radiation transport with this type of opacity, you bin the opacities in a certain wavelength or energy range. Everything within this energy range is going to be kind of averaged together, and so on and so on and so on. So do I need to know the exact position of this energy if I'm going to bin it? Probably not. Do I need to know the height to some percentage? Yeah, I probably want to know the height, because a factor of 2 could make a difference between a photon getting out or not. And we don't have measurements for those. We'd love to have measurements for those. Yes, well, this is all, these features are bound. I'm not quite sure. Yeah, that crazy detail. Let's go back. So these are bound features. Here's your Bremsstrahlung, so-called free. That's a photon scattering off of a free electron and giving up some of its energy, and the electron remains free, so it's called free. And here's your scattering. So it depends on where you are in the curve. The goal was to figure out where would gammas that start out here downscatter and eventually find an opacity low enough. So it has to go through. You could, yes. Well, this has all of the ion stages that are relevant for samarium, and we would see a similar plot for all of the other elements. So they're always, if they're in this range, the bound transitions are always going to be dominant. And ionizing from one ion stage to another, that's included in here. So that glitch there, that's the bound free edge. So that's where photoionization kicks in. There's another mechanism that's not on this plot that determines the opacity for higher energy scattering that I'm not going to talk about. Okay, so remember the observation had bluer light. It had visible light as well as infrared. This is just an example of how one can get that, a very simple example to illustrate how the opacities are important in this example. On the left, we have a pure neodymium case, and on the right, we have 10% neodymium in iron. And what's being plotted is the flux, which is, to me, the spectrum, as a function of wavelength for different times in the simulation. So starting at early times and later, you can see there's a shift towards longer wavelengths as time goes by. Then if you compare this so-called sample wind, where a wind is, to me, sorry, astrophysicists, it's just code for, we're going to put something else in there now through some mechanism. The neutrinos magically make this happen. The effect of including almost all iron instead of neodymium shifts the curve to bluer wavelengths. And this is just a very simple example. What we've got, 10 plus lanthanides and another 10 plus actinides that really need to be added in to simulate what the composition physicists, the nuclear physicists are telling us from that side. So this is a multidisciplinary problem. And we've started doing these types of simulations, and we do indeed see that mixing in the lighter elements in detail will create a bluer result. Now the question becomes, which one will match the observation, and can we get more observations to rule out certain models? Okay, what does the future hold for observations for neutron star mergers? LIGO was scheduled to restart in September. It's now being pushed out to, as far as I know, at least this month. I'm not exactly sure of when it's supposed to come back online. Something I failed to tell you early on is, which you may not know, the observation was made 1 week before LIGO was scheduled to be turned off. So it has scheduled maintenance, and we just got lucky that it happened to be on, and we got that observation. 1 more week away, and we would have missed it. Now, based on this single observation, the current predictions are that we will see 2 to 30 such observations of neutron stars, and that's based on the star formation rate of the particular galaxy in which the event occurred. This could be drastically wrong, though. That could have been a once-in-a-lifetime event. It was super close, which helped us to see it. Otherwise, the intensity of the light would not have been visible, or the gravitational waves would not have been visible. So I would say, from my atomic physicist perspective, nobody really knows in detail how many we're going to see. And when LIGO goes on, if this prediction is right, within a year or so, we will have 10 or so observations to start comparing with. Or we may hear crickets for the rest of our lives. I don't know. So far, there have been many different attempts to simulate, to model that particular observation, and people vary all kinds of things, such as the radiation transport model. The opacity calculations can be done in different ways, 1D versus 2D geometry, etc. And obviously, additional observations would help. So to stress the multidisciplinary aspect of this particular work, here you have FRIB, which can be used to measure cross-sections for all kinds of isotopes, which will be necessary for the composition modelers to predict what the abundances are. There's also the ejecta modeling people who use these cross-sections. There's the radiation transport models, which again is a completely separate talk, which uses the atomic physics. From my perspective, from atomic physics, it's important for us to get these opacities out to modelers so that they can use them in different approaches, not just at Los Alamos. So we're in contact with NIST colleagues to try and get those out there. And a plea to folks who do laboratory astrophysics here and in the rest of the world, if anyone could measure lanthanide and actinide opacities at 1 eV and 10 to the minus 13 grams per cc, that would be fantastic. That may not be realistic, I'll throw in another wish list since I'm sitting here. As I was talking to Jaydeep earlier, if you could not only measure one lanthanide, but put in the right mixture of lanthanides we think exist, that would be great too. But I'll take just one if you can measure it. So as you can imagine, that density is kind of low. That temperature is often reachable, but that's kind of a low density. But anyway, that's the end of my talk. Thank you for listening.
I'm interested in what is the bottleneck that makes these calculations hard? Like, yes, 100,000 by 100,000 or like a million by a million, that's very big. You can imagine if it was perfectly parallel, then on massive computers you could do it. So I guess I'm curious what's the bottleneck in like scaling? Is it just like the codes just weren't used for that and they haven't been developed at that level?
No. So that's I would say that's the right number of levels. Now it becomes the fidelity, the accuracy of the calculation. Okay. Now we're using, I'll throw out Hartree-Fock type calculations, and so that connects to the question about accuracy of the energy level, the position of the line, and the height of the line. It's not good enough. You have to have another theory, and those codes or theories are very intensive and maybe not embarrassingly parallel.
Okay, so basically there would be, what I'm hearing is there wouldn't be much utility in scaling out more.
Mm-hmm. Yes. Now for the neutron star modelers, they are already parallel and they're hitting brick walls that 3D is the holy grail there, but it's very difficult to simulate such a large object.
So we talked about this earlier about statistical approach of calculating movies, but now as we were talking, we triggered another question. Are there any experimental efforts to get, instead of counting levels of low energy, in fact, get statistical?
Are there experimental? Not that I'm aware of. I've only seen calculations statistically for lighter elements and no experiments to back it up. They could be out there, but I've never seen them. Anyone else? You're all experts in atomic physics now.
So I had a question. You talk about doing calculations for just one element, but in reality, like it's some horrible soup of everything.
Right.
So how do the opacities how do you join them together?
Okay. So there's a standard theory if you're an LTE that what you have to do is say, okay, I've got this percentage of this percentage of this, percentage of this, and they share a common electron density cloud. So this element gives up so many on average electrons in this one, and you iterate to find the one common electron density that satisfies temperature and pressure equilibrium. And once you find that, you add the opacities at each one of those respective conditions to get a total opacity. You weight them by the mass fraction, and you're essentially evaluating them at an effective density, a different density of each one. Even though the whole thing might have a single density, they each have their own special density as far as opacity goes. And that's a fairly developed technique. If you go to our website, it will allow you to mix and match the first 30 elements to your heart's content, and that's what's going on under the hood there.
Do we know what is the impact in the opacities for going beyond the
Do we know what?
What is the impact in the opacities?
Yeah, so that's a great question. That's yet another talk, but I've taken a shot at looking at non-LTE physics, and it could potentially change the opacity by an order of magnitude. And it would be less ionized, so it would be more neutral. So it would be dominated by the neutral ion stage, which offhand I can't remember if that would increase or decrease. I just remember an order of magnitude. And that's just me guessing at what I think the non-LTE conditions would be, because I don't have a modeler handing me what is the radiation field here. It's still coming from codes that are rather bulk in this assumption. But that's something I'd love to explore.
So do you think it's more probably a shift in the total magnitude rather than a change?
I think it could result in spectroscopic features that don't exist rather than just a bulk change in the light curve. But that's just me looking at opacities rather than handing it to a radiation transport person. It's kind of difficult to know ahead of time.
Any other questions for our speaker? All right, if not, let's thank you.
Okay, thank you.